everyone, this is Dr. Sandeep, working as Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about the crystallographic directions. In the previous session, we have discussed about the what is the polymorphous material, what is an allotropic material, and what is the importance of these allotropic and polymorphous material. So in that session, we have discussed about the how to find out the atomic packing factor and what is the importance of this atomic packing factor also we have discussed. Now, after discussing all these things, now the next thing which is very important in the crystallography is nothing but the crystallographic direction. So, based upon the direction, that means whether it is moving along x direction or y direction or z direction. So, based upon this direction, we can easily tell that how much distance the crystal or the unit cell is being shifting towards x, y or z axis. So based upon these x, y, z coordinate axis, we can easily find out the directions of the plane, as well as we can easily locate any point given in a unit cell. Suppose if you want to specify any point in a unit cell, so without any reference axis, we cannot find out this any point given to us. So that's why the crystallographic directions are very important in identifying any point in a unit cell, or also to give the directions along the XYZ coordinate axis. Now we'll see how to look at all these things. Crystallographic directions, points as well as planes. So these are very important in order to give the values of any point which is lying on the unit cell, as well as on which plane, whether it is lying on x plane or y plane or z plane, and also in which direction it is moving. So all these are very important in this crystallographic. So based upon the crystallographic directions, we can easily identify which point where it is located based upon the coordinate axis. Now when dealing with crystalline material, it often becomes necessary to specify a particular point within a unit cell. So if you want to specify any particular point in a unit cell, so these crystallographic directions are very important. Suppose I have a unit cell like this. I have to locate a point P in this unit cell. So without any reference axis, I cannot specify the position of the point from which axis it moves. So if I have the directions along XYZ coordinates, so this is X coordinate, Y coordinate and Z coordinate. So if I have this reference axis, and from this reference axis I can easily identify what is the distance from X axis, what is the distance from Y axis, and what is the distance from Z axis. So in this way I can easily tell the coordinates of the point P with reference to the coordinate axis. So that's why the coordinate axis is very important in specifying a particular point in a unit cell. So that's why to study the importance of these coordinations, crystallographic directions, points as well as the directions, to specify any particular point, we need to have a reference axis. And labeling conventions have been established in which three numbers or indices are used to design the location, direction as well as the plane. Now here, what is the criteria or what is the norms we are following to give all these location of the points, directions as well as plane? Means we have to use here three numbers. So three numbers are nothing but the indices. So it will indicate along which point you have, along which directions you have, as well as which plane it is lying. So suppose in this unit cell I have a point P again. So this point I have to specify where the point is being located, which axis it is located. So I'll write it as X. So at X position the point is being located. Next, the direction along Y direction or Z direction or X direction. So that you have to show. Next, on which plane it is lying. So that is the Z. So this is how you have to represent the position of the point P in a unit cell based upon the three indices. That's why it is called as a three numbers or three indices, which is used to designate the point location, the directions as well as the planes. Now the basis for determining the indices value in the unit cell with the right hand coordinate system, which consists of these three XYZ axes. So these XYZ axes are very important in order to identify the position, the direction, as well as the plane of the point in a unit cell. So without the reference axis, we cannot find all these things. That's why the coordinate axis, which is having the XYZ axis, this has to situate exactly onto the location of the unit cell. So that's why it is very easy to us to locate the position of that. So what is happening here? What are the axes you are having? The coordinate axis. This is the XYZ axis. Whatever the axis we have. So this axis, one of the corners has to coincide with the unit cell. So I have a unit cell like this. I have a unit cell like this. So in this unit cell, one of the corners, so any one of the corner, either this or this or this, any one of the corner has to coincide with your coordinate axis. That's it. If I shift this unit cell here, so how I will get? See clearly here. I'm drawing the coordinate axis like this. So this is how I have a unit cell like this. This is the unit cell without any reference axis. So this figure is without any reference axis. Now the same figure, I have to reflect this figure where one of the corner has to coincide with the three coordinate XYZ axis. So I am shifting this unit cell along the XYZ axis so that I can easily locate my position of the point in which axis it is lying, on which coordinate it is lying, as well as in which plane it is lying. So this is how the complete picture is look like this. Now again, if you find out the angle between the three axes, so alpha is the angle between the y and z directions, and beta is the angle between the z and x axis, and gamma is the angle between the y and x axis. So the angles, alpha is the angle between the y and z axis, beta is the angle between z and x axis, and your gamma is the angle between the x and y axis. So based upon these three axes, you can easily identify the position of any point given to us. That's why the location of the point is very easy for us to identify when you have these three reference axes, that is the XYZ axis. And for second criteria is what? We have to locate any one of the corner of the unit cell to the coordinate axis. So this is how you have to design your unit cell, which is exactly coinciding to the coordinate axis. So it is very useful. It is very easy for us to identify any position with reference to the given XYZ coordinate axis. Now, if we consider a small example like a point coordinates, the position of any point located within the unit cell may be specified in terms of the coordinates as a fraction of multiples of the unit cell. So, what are the point we have? If you want to locate the point of the unit cell with respect to the coordinate axis, what we have to do? We have to specify in terms of the coordinate axis. That means the position P has to locate from the reference axis either x, y, z direction. So this point P, at what distance from x axis it is moving? Similarly, at what distance from y axis it is moving? Similarly, at what distance from z axis it is moving? If you know the distances along x, y, z directions, then it is very easy for us like this. Then it is very easy for us to find out the distance of that point P from all these three reference axes. So I'll find the distance from along x, along z, along y. So that's why I'll get all the three coordinates of the position of the point like this. Now if you see here in this example, it is very clear to elaborate this example. I have a position P here. That is I have to locate the position of the point P. Now I have a unit cell. This is my unit cell which is having the sides A, B and C. These are the three edge lengths of the unit cell. Now I have the, see, first point is what? We have to place the unit cell in with such a way that one of the corner has to coincide with the coordinate axis. Now you have to check whether any one corner of the unit cell is being coinciding with the coordinate axis. Now if you see here, yes, this corner is exactly coinciding with the coordinate axis. The edge are clearly coincide with the coordinate axis. That means the first point is done. Now, coming to the next point, I have to know the edge lengths, that is the edge length along the x-axis, y-axis and z-axis. Now, if you see the edge length along the x-axis, so along the x-axis, edge length is a, that is the distance, that is the unit length. A is the unit length along x-axis. Similarly, along, if you see the y-axis, so this is my y-axis. So what is parallel to y? B. So B is the unit length along y-axis. Now you see, similarly the z-axis. So if you see exactly which is parallel to z, it is C. So C is the unit length along the z-axis. So that means I have a edge length, that is the unit length along x-axis is A, along y-axis is B, y-axis it is B, and z-axis it is C. So these are my unit length along x, y, z axis. Now, what is the next step? First step is what? We have to coincide the coordinate axis for the one edge of the unit cell. The second one is you have to identify the unit length along the x, y, z coordinate axis. Now, after that, I have to locate the position P, that is the point P here. So this is my exact position of the point P. Now, what I have to do? The third point is what? The third step is what? I have to locate the distances. I have to calculate the distance along the x, y, z axis with reference to the unit lengths. Now, suppose I have a point P which is having the QRS as my coordinates. So what I'll do here, see here, in this manner which I have the QRS are the coordinates of the point P. I will assume that the coordinates of the point P as QRS here within the unit cell. Now what I have to do, I have to determine the fractions now. How to determine the fractions? If I know the unit length distances, then it is very easy for us to find out the fractional unit length of the point P. I have to multiply with the unit length distances. So now this point P, from this point P, I'll drop along the z-axis, and also I'll drop along the y-axis, and I'll drop along the z-axis. So this is how. Now if you see here, the distance from point P to x-axis is exactly parallel to your z. So what is the distance here? S is my, so QRS is nothing but QRS are nothing but your ABC, the unit length distance. So I will just multiply S into C, R into B, and Q into A. So Q into A is my distance along X, so which is parallel to X. So that's why it is QA. So this is X. So X again, X, Y, Z. Okay. So along x-axis, it is QA. So that's why along x-axis I have written as QA. Now along y, what is the distance? R into B. So this is R into B along y. And along z, it is S into C. So I got the distances. Now Q into A is the distance, that is the fractional unit length along the x-axis. And R into B is the fractional unit length along the y-axis. And S into C is the fractional unit length along the z-axis. So this is how you have to locate the fractions. So the Q coordinate, which is a fraction corresponding to the distance of QA along the x-axis, where A is the unit cell edge length. So all the edge lengths here we have A, B, C. So A, B, C are my edge lengths along x, y, z directions. Now the respective R and S coordinates for the y-axis are also similarly identified. So we have to draw a table so that, so what I'll draw here, so you draw a table like this. So totally you have 3. So divide into 3 columns. Now I have x, y and z are my 3 reference axes. Now what are the coordinates of your point P? My point P coordinates are Q, R and S. And of course, you know the unit cell edge length. So what are the unit cell edge lengths? Along x direction, if you see in this, along x direction, what is the edge length? So this is my x direction. So this is A. Along y, what is the edge distance? B. Along z, it is C. Simple. Now you have to multiply these two, so in order to get the coordinates of the point Q. So that is the fractions of the point P corresponding to the edge length. So Q into A, you have to just multiply Q into A, R into B and C into S. So these are my, so you can see clearly here QA, RB and SC. So this is how you are getting the fractions. Now, if you see step by step here, we specify the position of P in terms of the generalized coordinates Q, R, S. So, you have to specify the coordinates of the point P. So, here we are specifying clearly the point P coordinates as Q, R, S. So, where Q is the fractional length along the x-axis. So, clearly you have to know at what directions your distance, that is the unit length, is exactly parallel to each other. So, here exactly the Q is along the x directions. That's why x. So r is some fractional length along the x-axis, as well as b is along the y-axis. Similarly, s is along the z-axis. So after knowing the distances along x, y, z coordinates, then it is very easy for us to find out the fractions along the 3 coordinates x, y, z. Now, thus the position of the p is designated using the coordinates q, r, s. So whatever the point is given to us, so the point has to designate by using these coordinates q, r, s. But generally what we'll do, we'll put the commas. So you should not give the commas in between. So this is the representation of the coordinate points in the crystallographic directions as well as the planes. So this you have to remember. So what is happening here? We have to designate the position of the point P with these 3 coordinates Q, R, S with the values which are less than the equal or unity 1. So why it is less than or equal to unity 1 means, so what are the unit cell we have, it is exactly equal to A, that is unit cell, the 1, B is also 1, C is also 1. So exactly it is equal to 1 or less than 1. So in such a way that you have to find out the values of the P value. Now further we have to choose not to separate these coordinates by commas. So as we discussed, so we should not give the commas in between these coordinates. So generally we'll do this mistake. So this we have to avoid. So this is the wrong direction. So what we have to do? We have to show the point P in like this Q, R, S without comma. So this is the correct representation. And also what we have to do? We have to close them in the square bracket. So this is the 2 criteria you have to remember. So you should not keep commas or punctuation marks in between these coordinates. So what are the things you are showing here? Suppose the Q, R, S. So this is wrong representation. Q, R, S. So this brackets also is not correct. So this is also not correct. So the representation is the square brackets with these coordinates. We should not separate it by any commas or punctuation. So this is how you have to represent the position of the point P in the crystallographic directions. Now if you see the problem here, if your location of a point having a specified coordinate. So in the unit cell given to us, we have the distance along the x, y, z directions. That is, along x direction it is given as 0.48, along y direction it is given as 0.46, along z direction it is given as 0.4. So these are the unit cell lengths along x, y, z directions. Now for this you have to specify the point which is having the coordinates of 1 by 4, 1 and 1 by 2. So based upon these, that is, somewhere you have a point P which is having the coordinates 1 by 4, 1 and 1 by 2. You have to look at this point. That means we have the values of the point P, that is QRS values I have, and I have to locate the point P. So again, what is the first thing you have to do? We have to check whether any one edge of the given unit cell is passing or which is coinciding to the coordinate axis or not. Yes, this is exactly at the one edge is passing through the coordinate axis. Now, simple logic is to we have to draw the table. All the three axes we have to represent here: x, y, z. And what are the positions of the point P given to us? It is 1 by 4, 1 and 1 by 2. Now I have to represent the coordinates of the point P with the help of the edge lengths given to you. So what are the lengths? Unit cell length along x direction. If this is the x direction, so what is the distance along x direction? You have to see parallelly. So this is exactly parallel to this. So both are parallel. That means this is along x. So this is 0.48. So similarly, what is the distance along y? So this is my y direction. So what is parallel thing? So 0.46 is exactly parallel. And what is z here? Z is exactly parallel to 0.4. So in the previous session slides, we have seen what is the distance means P into S. That is, these two you have to multiply 1 by 4 into 0.48 and 1 into 0.46 and 1 by 2 into 0.4. So this is the coordinates what you are getting for the point P. So we'll see how to show all these things now in the next slide. See the solution here from the sketch. Edge length of the unit cell follows as A is 0.48. So the distance along in the figure, in the previous figures, we have seen only the ABC values. Okay, so this is the A. A is given as 0.48, B is 0.46, and C is 0.4 nanometers. So this is the edge length of the unit cell along x, y, z direction. Now, further if you proceed, the fractions what we are given, the QRS values as 1 by 4, 1 and 1 by 2. So these are the points given to us. Now from this we have to locate the position of the point with reference to the coordinate axis. So what we do here, therefore first we move the origin of the unit cell. Point M, that is Q into A, that is 1 by 4 into 0.48. How much you are getting? 1 by 4 into 0.48. It is approximately 0.12 nanometers. So this is the first point. Similarly, you have to multiply this R into 0.46 and this is 0.4. So now see here clearly you can get. So we proceed, the RB is equal to 1 into 0.46. So along the Z, Y directions you have the point P. So it is 1 into 0.46. So you'll get 0.46. Now parallel to the Y axis. Now from point P, N to O. So from point N to O direction. So what is the distance covered here? It is 0.40. So 0.40 into 1 by 2, you are getting 0.2 nanometer. Similarly, along Z direction also same thing. So like that, if you multiply these directions along this direction, this and this, you are getting the position of the point P. So we are converting the given unit cell with all the three coordinate axes and also given the unit cell lengths into the point P with QRS values. So how to locate the point, at what distance the point has to move. Now the point from the origin, you have to move a distance of 0.12 nanometer along x direction. So that's why you're getting along x direction. Now from point N, you have to move along 0.46 value along the y direction. So exactly along y. From point O, you're raising to 0.2 nanometer along the z direction. So this is the point P. So this is the location of the point P with the given units length as well as the coordinates of the point P. So how to calculate the lengths, the edge lengths, at what distance you have to move along x direction, y direction, z direction. You have to. This is the thing you have to identify. Coming to the next thing, specification of point coordinate. Specify the point coordinate for all atom positions for a BCC unit cell. So this is the body center unit cell. So for this body center unit cell, you have to specify the point coordinates of all the atoms. So for all the atoms, you have to show the point. So how to represent these points? Again, you have to follow the same rule what we have followed for the identification of the point in the unit cell. Similarly, given the any unit cell, first you have to see whether the unit cell is one of the edge of the unit cell is passing through the coordinate axis or not. So that is the first criteria. So after checking whether the coordinate unit cell is exactly passing through the coordinate axis, then from the reference axis, it is very easy for us to find out the distance or the location of any point given in unit cell with reference to XYZ coordinate axis. Now in this case also, for the BCC unit cell, we have to locate all the positions of the point with reference to XYZ. Now totally how much you have, how many points you have here? First point, second point, third, fourth. Since it is a BCC body centered, fifth point, 6, 7, 8 and 9. So total 9 points we have. So for these 9 points, we have to give the position of all the points with reference to XYZ axis. So what is the procedure? We'll see. Now again, the point coordinate for the position number 1. So first position, since it is exactly at the origin, so all the XYZ coordinates will be 0, 0, 0. So this is the position of the first point. And since it is located at the origin of the coordinate system, therefore the fractional unit length. So what is the fractional unit length here? I have along A, X is A, B is A, C is also A. X, Y, Z. All the edge lengths are same at X, 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 A. Now what are the coordinates here? 0, 0, 0. So what is A into 0? A into 0, A into 0. So all are 0, 0, 0. So all the points at the point 1 are zeros, since it is exactly lying on the origin. Now coming to the slowly, if you move from point 1 to 2, what is happening here? Along x direction, you have a unit length of A. So A into 1. So this is A. But since it is A equal to 1, the unit length, so it is 1. So along y direction, there is no value. So y is 0, z is also 0. So 0, 1, 0, 0 is the position of your position of the point P2. Slowly, if you move to the third position, what is happening here? The position 3. Along x direction, you have 1. Along y it is 1 again. There is no distance along z. That's why it is 1, 1, 0. So this is how you have to bring out a table so that it will have a clear idea. So this is the following table representing the fractional unit length based upon the XYZ axis and the corresponding to the point coordinates of the distances for all the 9 points. So first we have to show all the points what we have 1, 2, 3, 4, 5, 6, 7, 8, 9 points in the BCC unit cell. Now fractional lengths along XYZ directions of each point we have to show. Along XYZ directions, what are the fractional length along x direction for the first point? Since it is exactly located at the origin, you have all the positions as 0, 0, 0. So x is 0, y is 0, z is 0. So how to represent the point coordinates? As 0, 0, 0 with the closed bracket. So we are not specifying the distances, or we are not giving any commas in between. So without commas only we have to represent. If you see the position point 2, so what is the distance along the point 2? Only along x direction we have. We don't have any distance along y and z. That's why it is 1, 0, 0. Coming to the point 3, you have along x, along y. There is no distance along z. So 1, 1, 0. Coming to the fourth point. This is the fourth point. What are the distance you have? Along x direction, you don't have any distance. So that's why it is 0. Along y, you have 1. Along z is 0. So that's why it is 0, 1, 0. Now coming to the fifth point is exactly at the midpoint. So along x direction half, y direction half, z direction half. So 1 by 2, 1 by 2, 1 by 2. So this is how you have to represent. Similarly, 6th point again along z x axis there is no distance. Y no, z s. So 0, 0, 1. Seventh point, if you see here, it is 1, 0, 1. Eighth point, since you have in all directions along x you have, y you have, z you have. So that's why you have 1, 1, 1. Again, coming to the ninth point, only along y and z. So this is how you have to represent any given unit cell, whether it is a BCC or FCC. First thing you have to know, you have to exactly check whether the any one edge of the unit cell is exactly matching to the coordinate axis. From the coordinate axis, you have to identify what is the unit cell length distances and also along xy directions. From this, you have to multiply the total length of the distance of the point P which is located. So this is how you have to represent. Now coming to the crystallographic directions. So again, the same thing you have to follow for the crystallographic directions also. What is the first point here? Vector of a convenient length is positioned such that it passes through the origin. So always origin is very, very important. If you want to tell any point specifications, the origin is very, very important. That's why the position of that has to pass through the origin of the coordinate system, and any vector may be translated to the crystal lattice without alteration or parallelism which is maintained. The second thing is what? The length of the vector projections on each of the three axes has to be determined. So we have to identify what is the distances, or we have to determine what is the distance along x, y, z directions only. When you know the distance along x, y, z directions, then it is very easy for us to specify any point along the unit cell. So this is the second thing what you have to know. That means these are the measured lengths of the unit cell. That is the ABC, whatever the ABC values which are given in the unit cell. So that is the second point. So these numbers are to be multiplied or divided by a common factor to reduce them into small integers. Suppose in some cases, if you're getting the higher numbers or any fractional numbers, so these fractional numbers has to reduce to small integers by multiplying or dividing by any integer. So this is the thing what you have to do. That is the third point. And coming to the fourth point, you have to show the indices. That is the how much values are there in the square brackets which is not separated by comma. So 1, 1, 0. So this is the representation. 2, 1, 0. So this is how you have to represent. So first point is what? You have to check whether the given unit cell is coinciding with the coordinate axis. The second point is what? You have to find out the edge lengths with respect to the unit cell lengths ABC. And third point is what? You have to reduce the given value into small integers by multiplying or dividing with the common factor. And finally, the fourth point is what? You have to close the given values in the closed brackets without giving any commas. So this is the four points you have to remember in specifying any given thing. Now, if you see this example, for each of these three axes, which exists between positive and negative. So any axis has a positive value as well as negative value. So how to indicate the positive direction as well as the negative direction here? So in this case, all the points are along the positive, so that's why it is 1, 1, 1 or 1, 1, 0 or 1, 0, 0. But in some cases, it may come along the negative direction of y, negative direction of x, negative direction of z. So how to represent them? So this we have to represent by giving some bar. That means close brackets 1, 1 bar 1. That means you have a value of the point P along x direction, it is 1. Y direction you have minus 1, that is 1. Negative direction it is moving. Similarly, along z you have 1. So x and z are positive directions and y is along negative direction. So in such a way that you have to represent the point based upon the directions, whether it is positive or negative. So any point, any coordinate axis which has a positive as well as negative directions. So based upon the directions, you have to specify clearly where is the position of the point based upon the reference axis. So in any case, if you see the dash thing, the bar thing here, that means it represents a negative value, that is the negative direction either along x direction, y or z. So in this way, you have to represent any point in the unit cell of the crystallographic things. So in this session, we have learned about how to locate any point in a unit cell. based upon the coordinate axis. So coordinate axes are very, very important. So based upon the coordinate axis only, we can easily identify the location of the point. Also, we have discussed about how to locate any point in a given BCC also. For a given BCC, that is body centered unit cell, cubic center, any position we have to mention it based upon the 4 points. So what are the 4 points we have to consider here? The first point is what? We have to see whether the any one edge of the unit cell is coinciding with the coordinate axis of XYZ. So that is the first point. The second point is what? We have to determine the edge lengths. The third point is what? We have to reduce the given values into small integers by multiplying and dividing with a common factor. So that is the third point. Coming to the fourth point, we have to show that position of any point with the square brackets, and also we have to not give any commas or semicolons in between. So this is the representation of any position of any point in a coordinate unit cell or a crystallographic direction. So these are the very useful to represent any point in a given unit cell or any type of atomic structure. And we have discussed about the how to show the crystallographic directions in a plane, points as well as the directions. So these are some of the references books where you can find the information about all these topics what we have discussed. First one is the Introduction to Physical Metallurgy by Sidney Havener. The second one is Essential of Material Science Engineering by Donald. The third one is Material Science and Metallurgy by Kodigiri. And the fourth one is Material Science Engineering by William Castro. So these are some of the references books where you can get the information about the detailed note of how to identify the directions, planes, and the points in any crystallographic given unit cell. Thank you for the session.
Like, share and subscribe. Hit the bell icon for more updates.